So let's talk about the motor market today. So on the agenda, a number of different topics. Motor efficiency terms. Today in the motor market, there are all kinds of efficiency terms that are being thrown out by people. And the sales and marketing people use these to try to confuse people or blow things past them. Standard efficiency. Many of us with gray hair in the room grew up having standard efficiency motors and a different category called high or energy efficient motors. Today, standard efficiency motors no longer can be bought new. Starting in 1992, the government, the Energy Policy Act, said we're going to draw a line in the sand on efficiency, and anything that used to be a standard efficiency motor can no longer be manufactured. Let the manufacturer sell what they already had made, but they couldn't make more. So those motors in the new motor market went away. Still lots of them out there in facilities. Another efficiency related term is nominal or quoted efficiency. This is the average measured value of a large number of motors of the same make and model. This is the number that's required by NEMA to go on the nameplate. So when I'm looking at the nameplate over here and it says efficiency, that number that's stamped there was the average of a large number of statistical sampling off the assembly line of that make and model motor. So typically, let's say they had to check, NEMA says you had to check 1,000 motors, test them for efficiency. So in testing the 1,000 motors, not every motor was exactly the same efficiency. NEMA says they can calculate the average, and that goes on the nameplate. Some companies will call that, instead of nominal, quoted efficiency, because if you ask them what the efficiency of that motor is, that number right there, that average, is what they're going to quote you for that make and model. Okay? So nominal, quoted, the same thing. Now, we're starting to see on motor nameplates minimum or guaranteed efficiency. NEMA requires nominal efficiency on the nameplate. There's nothing that says minimum or guaranteed efficiency has to be on the nameplate, but some manufacturers are looking at that, putting it on there. Notice in my example, guaranteed efficiency is slightly smaller than the quoted or nominal efficiency, the average. So in testing 1,000 motors, do they have an idea from a statistical sample of what the high and the low looks like in general? Yeah. So they're basically saying, as a marketing means, a sales means, yeah, there's the average, and this is the lowest we would expect any motor of that make or model from our manufacturing facility to be. Okay? And now here's the marketing part. If my competitor won't put that on their nameplate, what does that tell you about their crappy manufacturing methods and substandard materials and the difference between their average and their lowest possible motor they can make off their assembly line? You see how that becomes marketing and sales at that point. We didn't have a big difference here, so we're going to try to play that up in selling and marketing our motors, because we're going to tell you that every motor you get from us is going to be really close to that number because of our superior manufacturing techniques and our quality materials that go into every motor. Okay? Not required, but you're starting to see some companies do that as a sales and marketing means. Premium efficiency. Now, when I started out doing motor classes for folks in the 1990s, premium efficiency wasn't defined. And if it's not defined, sales and marketing can call that whatever they want. Starting in 2007, premium efficiency is the NEMA term we use for what us gray hairs used to call high or energy efficient motors. So when we took the standard efficiency motors away, what were high and energy efficient at that time now became the new standards, and the top of the line newest, best of the best, since 2007, we are calling premium efficiency. So the policy folks in the government changed the names. You still go, you look at the motor market, there's the top, the bottom, and a range. Used to be, if we had a cutoff line that was higher energy efficient and standard, now today we have high and energy efficient and premium. Standards doesn't exist. It rose by any other name. We still have highs and lows. Back before this became the standard, a major motor company, starting with the letter B, who I shall not name, really took some heat for taking their standard efficiency motors and on the assembly line putting a sticker on the box that said premium efficiency. And people say, you can't say the motor's in the box is premium efficiency, it's a standard efficiency motor. And remember, it wasn't defined by NEMA at the time. And the company started with the letter B, which shall remain nameless, said, oh, we weren't saying the motor inside the box was premium efficiency. We just wanted people to think about premium efficiency. Yeah, sure. So now that premium efficiency has been defined by NEMA, motors above a certain efficiency at that horsepower level, the marketing folks had to come up with a new marketing term. So what they seem to have settled on now, because they can't use premium outside of its definition, is ultra high efficiency. When you buy a motor that says it's premium efficiency, you know it meets the NEMA criteria. Do not buy a motor based on a label that says ultra high efficiency. Because what's better than premium? Ultra high. Yeah, that becomes the new marketing term out there. So they always have a marketing and sales term that they have to come up with that's not well defined. It's important to remember when we're going into an energy efficiency project looking at motors, replacement, higher efficiency, we want to use the defined numbers, not the sales and marketing number names. Now, the biggest thing that I want to relate to you that I've seen in my going out for insurance companies and utilities and attorneys and individual companies that hire me to come out and look at why they're having motor issues after they do their retrofit and put in their new energy efficient motors. It's not that the motors aren't necessarily saving money, but they're having operational issues with the new motor and the equipment they're driving they didn't have before. And that's because these newer premium efficiency motors have slight operational differences and characteristics than the older motors that they replaced. And a lot of times, again, much like looking at power factor, nobody bothered to notice that this new motor runs at a higher RPM than the older motor, or has a higher inrush current and causes a bigger voltage drop when it starts than the older motor. So operational differences in these newer motors become important. Higher operating speeds in general, lower slip, which means they're stiffer motors in motor jargon. They don't slow down as much as the load increases. Anybody think of an application where if the load goes way up, increases a whole bunch, I want that motor to slow down as that load's changing? In my Texas market, pump jacks. What am I doing with a pump jack in the drivetrain? Gravity helps it bring it down the hole, and then all of a sudden, simultaneously, I change directions and I go from no load to lifting crude, loading it up and changing directions. What happens when I go down there and I add that load of crude at the bottom and change directions and I don't slow it down? I'm jerking it back up. What happens when you jerk drivetrains? Ask my twin sons about, jerking drivetrains and transmission problems. And so that becomes one of those, if you have applications that really need what we call low slip motors, design D motors in the NEMA type, that when the load changes, the speed of that motor changes significantly, so we're not jerking drivetrains and messing drivetrains up. And I put one of these new premium efficiency motors on that drivetrain. 8, 9, 14 months later, we have a bad drivetrain. Drivetrain problems. So I've seen a lot of that type of thing. Are premium efficiency motors really efficient? Yes. Does it make sense to put a premium efficiency motor on a low slip application? Only if that premium efficiency motor is a low slip motor, or excuse me, high slip motor is what we want. I can buy premium efficiency motors that are low slip and high slip. How many people do you suppose look at that application to say those motors that were high slip need to be replaced with a high slip motor? Now we're putting these low slip motors on there, and then you know how us consultants are. I'll come out and get the billable hours and give you my bill to tell you, you put the wrong motor on there. You need to go get a high slip motor with the same efficiency. I'm not going to fault you for putting a premium efficiency on there. You just didn't look at the operating characteristics. They also have higher inrush currents, and sometimes we're seeing larger physical sizes. And that's important if it's coming out of a tight space. So motor speed and slip. Older standard efficiency motors had rated speeds between 1710 and 1740 for your standard 4-pole 1800 RPM synchronous speed. Newer premium efficiency motors have rated speeds between 1770 and 1790. What happens when I take a 1710 RPM motor out and replace it with a 1790? Is 80 RPM important for my flow output on a fan, pump, or compressor? What did I just do to my output on a pump? I increased it. Now, for many applications, I hear people say, yeah, we put in this new motor and it increased flow, and that was good because we needed some more flow. More flow is good. We can fill our tanks faster. Okay? So sometimes that's good. What happens when I took a 1710 RPM motor out on a conveying belt for a bottle capper and I put a 1790 in? We're not capping the bottles right anymore. That's a problem. Still an efficient motor. We have an operational issue now. So those are the types of things when you don't pay attention to RPM and speed. I've seen some places that when their flow out of their pump increased with the new motor, faster motor, they went and said their solution was to crank the valve closed because they wanted a certain amount of flow. Tighten it down, choke it down to get that flow back down to what it was meant to be. Okay. Now, if I don't do that, if I say, I take the approach, and this is really where my phone is wrong, and I go, oh, people have just not quite thought this through. I have the experience of having done through it before. We had this utility that gave us money to rebate new premium efficiency motors. We went out, we did those rebates, and our bill didn't go down at all. What's wrong? What did you put those motors on? Fans, pumps, and compressors. Did you notice your output on those devices went up? Yeah, we did. Our flows are up. Our airflow's up. Our liquid volume through the pipe's up. Okay, let's think this through. You put a more efficient motor on it. You didn't pay attention to the speed. It's now pushing more flow through it. What did that motor have to do to push more flow through that pipe? Draw more amps. But I'm more efficient than I was before. I've improved my gallon per minute per amp ratio, but essentially what I gained in efficiency, I lost in increased flow and increased power requirements, so my bill didn't change. That's one of those that's tough, difficult to tell to management. When the bill didn't go down after we did that big motor retrofit. How do you explain that? I have found that is, when we go in there, one of those big drivers of that. We're getting more flow. Okay. Was there a benefit to filling my tank faster? Maybe, maybe not. Depends on what the application was in doing those things. So that becomes important. Make sure if your existing motor is a high slip motor, that when you buy a new premium efficiency motor, it is also high slip and not a low slip. If you do not ask for a high slip motor, the motor company assumes you want the low slip motor. That's the standard. High inrush starting currents. Historically, if I asked a class like this, what's the typical percent inrush compared to running amps of a motor? I would hear 4 to 6, 4, 5, or 6. Okay? Can't argue with that. Many times, some of these newer motors are running typically in the 5 to 8 times the running amps of the motor on inrush or startup. Some I've seen as high as 12. If I take a motor out that was drawing 5 times its running amps when it started, and I put a motor in its place, a new premium efficiency, that draws 12 times the running amps when it starts up, what did I just do to the voltage in my facility when I start that motor? A lot bigger voltage dip when the motor's starting. Is that a problem? Could that be a problem? Could I drop that voltage now down far enough that PLCs and electronic controls lock up, trip off? I make money doing those calls as well. Phone rings, yeah, we got a problem. Okay. We have electronic controls tripping off now. We've never had a problem with these controls. They've been in for a while. Okay. Did you guys do a energy efficiency retrofit of some kind? Yeah, we put in new motors here, and that's about when the problem started. Okay. Well, did you pay attention to the inrush current in those new motors when you bought them? Why would we do that? Okay. Well, because these new ones have different ones. Okay, I'll come out, pay me to come out and show you on the nameplate what you needed to look at. Okay? It's good work if you can get it in terms of doing those things as a consultant. So that becomes important. Okay? So the key becomes, when I take that existing motor out, I want to look at that NEMA code letter on the nameplate and make sure that when I replace my new premium efficiency in there, that NEMA code letter is very close to the one I took out. That NEMA code letter essentially tells me about the locked rotor and starting current of that motor. So if I replace an old motor with the newer premium efficiency motor of the same design code design letter, my inrush current won't change hardly at all, which means my voltage dip when I start that motor doesn't change much. And I don't have to necessarily, if everything's working with all my electronics already, have to worry about getting my electronics to ride through a bigger voltage dip every time that motor starts compared to what the old motor was. Okay? So that's important. Don't confuse that with NEMA design type. NEMA design type is more about the start-stop torque characteristics of the motor. This is NEMA code. They both have NEMA in it. One is code, one is design type. They both use letters of the alphabet. So that's easy to do. So there's a table in the electric code, we'll see it in the next section, that gives, okay, what those mean. But basically that code, NEMA code or the NEC code letter, comes from the National Electric Code, and that tells us about starting amps of that motor, how big they are. So the motor nameplate becomes kind of that information place that we can look at about these operational characteristics. And as I said, I see enough problems, get hired enough places in as a consultant to figure out what's going on, that if these are the operational characteristics that I see people making mistakes in over and over and over because they didn't pay attention when they put that new motor in. They just said, okay, we need a premium efficiency, 10 horsepower, 460 volt, 3-phase motor of a frame size of X, so the bolt holes line up, without looking at any of the other stuff to make sure we're getting the same thing we had before. So there are some requirements on the nameplate. Everything on the left is required by the National Electric Code. So you go through and you look at a lot of those make sense for the National Electric Code that's looking at safety and fire protection. Okay? How do I size the circuit for the motor if I don't know the full load amps and the voltage and those things? There are many optional things the code doesn't require, but maybe the federal government or other standards organizations require, that you might commonly see, but the code, the NEC, doesn't require them. Okay? So service factor, enclosure type, frame size, connection diagrams. So now, common complaints I get with some of these newer motors when my phone rings. My motors, my new motors, my energy efficient motors, my premium efficiency motors are failing at frequent intervals or high rates. I get frequent nuisance tripping or shutting down that I never got with the old motor. And I hear this statement quite a bit in the last 10 years. These new motors, they just aren't as reliable as the old motors. Are they not using as good materials, or what's the deal? Okay. And when I start looking at those complaints and going out in the field, what I see is those are related to failure to protect the motor from unusual physical and environmental conditions. We're pushing the motor past its ability to cool itself, so it's burning out early. Failure to protect the motor from expected but infrequent variations in electric supply. Single phasing. Things of that nature. Use of newer electronic motor protection devices with trip settings more sensitive than normal variations in electric supply. How many of you are using electronic or solid state overloads to protect motors these days in larger numbers? I see some hands. Okay. Get rid of the old electromechanical heaters and thermal element. Got the electronic devices in there. And now, many of them I can adjust that overload trip setting. Some of those devices also come with a factory trip for single phasing, current unbalance, high and low voltage, frequency. And to protect the company's rear end on warranty claims, they set those trip levels that you cannot adjust tighter than real world settings. And their argument from nuisance tripping is, but we're protecting your motor really well. If that motor's tripping off 7 times a day, does management have the idea that protecting that motor that well is a good thing? Probably not. So that becomes another one of the challenges. One of those places that I see people screw up when they buy new motors is not paying attention to insulation class. So insulation class in a motor is also given by letters of the alphabet. And the deeper you go into the alphabet, the better quality or more heat resistant that insulation on the motor windings becomes. It used to be, when we had U-frame motors back in the 50s and 60s, early 70s, that you automatically got Class A insulation unless you specified differently. Today's T-frame motors, the standard in the motor market today, you get Class B unless you specify something different. Today, I see a lot of folks that use F, G, H, even some M, because of the heat that that motor is going to be exposed to, or the various operating characteristics that the drive is going to expose it to. And so we'll talk more about some of those, especially with drives, later. If I go to a deeper letter of the alphabet, my motor will cost me more because it has better quality insulation on the windings that will withstand a higher level of heat. Notice over here these 4 different classes. Winding temperature down here, it's exposed to, the insulation life in hours. When I go to a higher level insulation from A to B, I get more hours out of that for the same temperature when I start looking there. This was hit home to me early in my career. I got a call from a major global paper products and forestry, wood corporation, come over to East Texas and look at a kiln. And they were accusing the utility of giving them all kinds of voltage problems and burning their motors out. So the utility called me, we want you to go over there and take a look at this. See what you can come up with. So we get to kiln. And we get on the property and they're showing us this 20-year-old kiln of German vintage. And when you think kiln, what are you starting to think automatically about? Temperature. Okay? And this kiln had about 40 motors in it. It was all automated. It was a tunnel oven type of a kiln. Put a pallet of 2x4s, wet 2x4s in, come out the other end, moisture reduced, ready to go to market, package, put them on a truck. So it was 20 years old, and in the last month they had about 3 motors fail individually. And what happens with the kiln when a motor fails? You kind of want to let it cool down before you start going in to replace the motor. So they had lots of downtime to replace the motor in this. So they said, you know, if we do the math, that 20-year-old kiln, those motors are getting close to the end of their insulation life. They made the decision to change the rest of them out at one time. So they went down and they bought 40 new motors to bring out. They went through the kiln, it was shut down, changed all the motors out. Now we should be good for a long time again. Started it up. 2 weeks later, they lost 2 motors the same day. 3 days later, they lost a couple more motors. Now, being in East Texas and Aggies, their initial thought was, we must have got a bad batch of motors from that company. So they went across town to a different motor distributor and bought 40 new motors, went in, shut it down, and replaced all the new motors. Now we should be good for a while. 2 weeks later, a couple motors burn out one day, a few days later, another one. Okay, now it's got to be crappy power from our power supplier. So we get in there, I'm looking around, they're giving me the spiel of what's going on, what's happening. The smart aleck engineer from the university asked the question, what was the insulation class on those old motors that came with originally? And what was the response from everybody with me? Huh? What's insulation class? So then I said, okay, are the old motors around? Do you have a junk pile? Oh yeah, they're back at a big pile back at the back of the plant right now. We can get out there. Anybody want to guess, a hazard a guess of the insulation class, the motors that came with a kiln for wood drying? R. They were R. Insulation class R. As a consultant, these are ones you like because now I got my Big Chief tablet and a crayon out and say, okay, go buy 40 new motors with our insulation class. That'll fix your problem. Here's my bill, I want my money. You know, that type of thing. So I have seen that over and over. Does anybody ever pay attention to insulation class when they buy new motors? People that have been through a problem, people that are paying attention to what the motor's information nameplate tells us, that becomes really important. Okay? Duty rating, continuous or intermittent. Companies can play a little game with you there. Sears and Harbor Freight. When I look at the size of the motors and the horsepower rating on the size of that motor, I'm saying, gee, I've never seen a 5 horsepower motor that small before. Well, that's an intermittent 5 horsepower rating, not a continuous. And so you'll see that a lot on what I'll call the residential home shop market, where that air compressor comes with an intermittent duty motor as opposed to the commercial and industrial air compressor that comes with a continuous duty motor. What's the difference? That intermittent must be only operated continuously for a specified time, then shut down and allowed to cool down to ambient temperature before you start it again. Lighter windings and insulation, lower cost. Basically, Harbor Freight and Sears can take the normal 1 horsepower continuous duty and make it a 5 horsepower intermittent 15-minute motor. Okay? There's the, okay, I got to know what they're talking about with their ratings. Okay? Classic example I run into, The graveyard shift had a 10 horsepower motor on a piece of equipment go out, a conveying belt or something, and management's been on them to get their goals. Produce this much, we've got contracts we need to ship continuously, we want to hit, and everybody get their bonuses. What happens when a 10 horsepower motor burns out at 3 a.m. in the morning? Can't go to town and get one. Where do I find one to keep running? Oh, nobody in this group ever robs one off another piece of equipment we're not using? Don't tell me you haven't, right? Or at least seen it. So lo and behold, that air compressor motor is a 10 horsepower, 460, 3-phase, and would you believe the bolt holes line up? Frame size is okay. We're in business, okay? We didn't notice it was an intermittent duty motor. So 45 minutes later, now we lost our second motor. The smoke came out. You all know that your job is to keep the smoke in your motors, right? And your light bulbs and your electronics. Because if the smoke comes out of those devices in your facility, they're not going to work very well anymore, right? Yeah, old electrician's joke. Okay? And so I run into that. I hate to call that a no-brainer because people just haven't been trained to look for that continuous or intermittent duty when they rob a motor. But I see that a lot in terms of, and when that second motor fails quickly, then immediately we're back to who's getting the blame? Power supplier for having bad voltage, dirty power, etc. in those things. So that's where that rating becomes important. Okay? I always fuss at my kids because where do you use something, many in your facilities may have the same thing. Where might you find some intermittent duty motors? Overhead garage doors in your facility. Why would we put an intermittent duty on an overhead garage door? It goes up, it might stay up for a long time, and then later in the day, what's it do? It goes down. And it stays down for a long time. We don't need that continuous duty. Unless you have kids like me, up, down, up, down, up, down, up, down. That's not good on it, right? Think about transferring those ideas to your plant. Okay? Where could that become an issue? Rated voltage. Again, the motor's going to say on the nameplate. Notice here the questions I get about the rated voltages on motor nameplates. What's a 230 volt circuit? What do people normally say about that circuit for the number, the voltage? 220 or 240? What's the voltage at the outlets around this room? 120? Anybody want to throw out 110?
115.
Yeah. Utilities talk about 120 volt service at the secondary taps of the transformer. Electricians, in my experience around the country, talk about 110 outlets at the farthest outlet in the building. 110 is kind of a minimum. What happens between the secondary taps of the transformer and the outlet? Voltage drop. So, interestingly enough, the motor folks said, okay, are we going to go with the utility numbers, the 120, or the electrician numbers, the 110? Hey, let's make them both mad and split the difference. So I put a 115 volt motor on a 110 or 120 volt circuit. A 230 volt motor on a 220 or 240 volt circuit. You see how that works? Yeah. Okay. Not important, but it's just interesting from the fact of, okay, let's just split the difference. That's what we're going to call our motor NEMA voltages when we look at those. Those become important. Now, the more important part that I want to get to in that is, okay, now what's high and low voltage for a motor then? A NEMA motor must run satisfactorily within its warranty specs at plus or minus 10% of nameplate voltage. So NEMA says that motor will not have reduced life at plus 10 or minus 10% from the nameplate. Okay, so if I look at a 230 volt motor, 10% of 230 is 23 volts. That means I should go up to be able to run that to 253 volts at the motor and not reduce its life. Or I could go the other way, 230 minus 23 down to 207 and not reduce the life. There's the acceptable range that that motor will operate within its design specs as voltage varies. Now I get a question a lot, can I run a 230 volt three-phase motor on a 208 three-phase Y service? I've got a 208 three-phase Y, I've got a piece of equipment over here that I could put in there, but it's 230 volt three-phase. So in other words, can I take that 230 volt motor there and operate it on a 208 three-phase service? Am I going to get 208 or 207 at the motor? Probably not. Could, if I'm close to the substation or a voltage regulator. So in many instances, it'll run, but I'll probably get reduced life out of that motor because I'm really pushing that, particularly if I have 205 or 203 at the motor because of voltage drop on that service. Phase unbalance I find to be a bigger problem than low voltage. People will check the voltage and they'll monitor voltage to a motor if it's not getting good life. But phase unbalance is the one they forget about. And if I have an unbalanced three-phase voltage to a motor, it's going to have circulating currents in those three windings that creates additional heat above and beyond what it would with a balanced voltage. And so I see phase balance is important in many plants in terms of we're having some motor longevity issues. We go in, the voltage looks good, the utility's been in, the voltage looks good. We come in, we look at phase unbalance, and all of a sudden we say that's a terrible unbalance. Particularly when you turn certain lines on in the plant. I was in an Indiana plant, and we'll refrain from saying where, probably 20 years ago, and they had a line that had over 100 fractional horsepower motors, single phase, wired from the same leg of the system. What happened to their three-phase voltage balance when they turned that line on? That one phase went way down. And the complaint was we're losing motors. I wonder why. So NEMA says if your voltage is more than 1% unbalanced, you should be derating that motor and not running that motor up to its full nameplate power. NEMA says do not operate a three-phase motor above 3% voltage unbalance. I've got out to places that are losing lots of motors, not getting the life out. We should get 10 years, we're getting 3. And the motor's gone and it looks like it's a heating problem. The insulation is toast. That have 5 and 6 and 7% voltage unbalance. So that becomes one of those that we forget sometimes to check in terms of motors. Loose connections. A loose connection in that conduit box there could be a challenge. What's that going to do? Is that going to create an unbalanced voltage in the motor? Yes. So that becomes, again, problematic. Could that, if it was a bad enough loose connection, be like single phasing that motor? Sure, if it's bad enough. Full load amps, given on the nameplate. These are the amps that the motor should draw when it's fully loaded and supplied its nameplate voltage. How do most of you use that number in checking and troubleshooting out in the plant? I've got a motor that seems to be running hot. Somebody's complained about running hot. I want to know if it's overloaded. We've changed something about the operation it's driving. Is it still big enough? So we check the amps, right, and compare them to the nameplate. Okay. If we're under that number, fine. If not, now we have a concern that we're pushing that motor past its design. The thing to remember is that amps is at the rated horsepower. What if I have a service factor on that motor? If I have a service factor of 1.25, I can go 1.25 times that number before I'm outside its design spec. That's the important thing to remember about that. That is the amps at the nameplate horsepower. When I have a service factor, I have an overload factor that I can use on that motor to push it past the nameplate. Okay, so service factor, the amount of built-in overload capacity over nameplate, horsepower, and amps designed into the motor. So again, as I said, if a 10 horsepower motor with a 1.25 service factor, I can load it to 12.5 horsepower and not reduce the life. So how did they get 25% overload capability into that motor? Instead of winding it with B, they put F or G or H in it. And by putting that better quality insulation in it, what does that mean about its ability to withstand heat? Higher, longer. Okay? So I can get a service factor of 1, 1.1, 1.15, 1.25, 1.4. The higher the service factor, the deeper into the alphabet the insulation class on that motor will go. That's what you're buying. Why would motor manufacturers do that? Let's go to 100 versus a 75. Say I need 83 horsepower for a pump. If I put a 75 on there, I'm overloading that motor and voiding the warranty. Have you seen the price of 100 horsepower compared to a 75? So what am I tempted to do in saving budget money? Put a 75 on there and live with the reduced life. Okay. So the motor manufacturer said, okay, take our normal 75, but buy a service factor on that thing. So buy a 75 with the service factor of 1.15 or 1.25, and that's not going to be near as much money as buying a 100 horsepower with a service factor of 1. So if you look at motor prices, I can essentially buy the motor with the service factor cheaper than it can buy the next size of standard motor. That's the idea there. Design code letter, that's what we talked about earlier, starting amps. Indicates the motor's locked rotor amps, it's an indication of the starting current. Letters of the alphabet, as I said. And so in the National Electric Code, there's a table that corresponds to those letters of the alphabet that start to tell us about the kVA per horsepower for locked rotor conditions, which gets us into the ballpark for starting amps. So the deeper we go, the higher the starting amps are going to be for that motor compared to the running amps. That's what gives us a feel there. So make sure you're trying to, or unless you've done some calculations, replace an older motor with a design code letter with the newer motor fairly close to that, or you'll have a bigger voltage drop. Okay, that's the thing there. Motor failure factors, driven load, electrical supply, physical and environmental conditions. When I go out for insurance companies, for motor manufacturers, for utilities, for individual companies, and get hired as a consultant to go tell them why all these motors failed or why they're having problems, if it wasn't faulty from the factory, okay, so let's rule out faulty from the factory, design defects or manufacturing defects at the factory. Once we throw those out that are covered by warranty, what are the things that I see in the field where people are losing motors and are problematic? Those things. It could be bad power quality. It could be the way we're starting, running, or stopping the load. In many instances, it's we've pushed that motor past its physical and environmental conditions it was designed for. How many of you have heard this over the years from somebody, maybe somebody you learned the business from? If you can't hold your hand comfortably on the enclosure of a motor, it's overloaded. Yeah, I see some. This is true. This is completely true. If you can't hold your hand on the motor frame enclosure comfortably, it's overloaded. The problem is, this is not a highly precise calibrated temperature measuring device. It was probably overloaded long before you couldn't hold your hand on there. Okay? So that's the other side of the coin. Bearing failures, while not as catastrophic as a winding failure, become pretty common in some facilities. Most manufacturers have moved away from serviceable bearings to sealed bearings. And they find they have less bearing failures with sealed bearings as opposed to giving you a grease zerk to pump grease into. And the problem, if you look at having a grease zerk on the bearing so you could pump grease into and service it, is how many of the young folks do you see ever clean the tip of the grease gun and the grease zerk before they put the end of the grease gun on there? And then they start pumping away. And if there's some gunk on there, that's another technical term, right? Gunk. And I push that into that bearing, and then I run that motor at 1750 RPM or a speed like that, what's going to happen to that bearing fairly quickly? Yeah. You grind it down. It's not so good anymore. I had a student in my electrical energy management class, a junior class at A&M. We were talking about people over-servicing bearings. And I mentioned that I had seen motors that were pumped so full of grease they would not turn. And my general premise is, how do you know, how does the new person that you've given that job know when to quit pumping a bearing full of grease? When do I stop pumping? You all know the answer, right? Yeah, when it comes out the seal. If it's coming out the seal, I know I got some in there, and I'm probably, not going to get more in there without more coming out the seal, so I quit. Standard operating procedure. We all learned that at some point. If it came out the front seal, is there a chance it also came out the back inside seal? Do you know who wins when bearing grease and insulation windings touch each other? Bearing grease. So that grease will break down that insulation on those motor windings in that bearing, or inside that motor. And all of a sudden now we've got a premature motor failure. I've seen it. It came out the back more than it was coming out the front. And eventually we can't put any more grease in there and the motor won't turn. And I had a student who said, BS. I think you're making that up. About 3 weeks later, he came into class. He got right up before I was ready to start talking. And he said to the class, I need to apologize to Professor Stark for my BS several weeks ago in class. I work at the local cooperative feed mill, and yesterday we had to pull a 200 horsepower motor off the top of a leg and bring it down because it wouldn't turn. And when we opened it up, it was so full of grease it wouldn't turn, and when we cleaned the grease out, it was fine again. Okay. So again, those types of things. So use the right grease. If you have serviceable bearings, motor manufacturers have said their bearing failure warranty claims went way down when they switched to sealed bearings. That's one of the reasons they've done that. Here is one that I see a lot of people in certain parts of the country have issues with. Okay, physical environmental. NEMA says if I operate a motor at an altitude that less than 3,300 feet, that's normal. If I'm above 3,300 feet, I need to derate the motor. Why do we care about altitude? What happens to the density of air as you get higher in altitude? It's thinner. And it can't cool as well. So the motor is designed to cool itself up to that altitude. Above that, I either have to derate the motor and not put as many horsepower on it as it says, keep the amps down, or add a cooling fan to dissipate that heat. A temperature of less than 104 degrees Fahrenheit ambient around the motor when it's running. Do any of you have any applications you can think of in your facilities where when a motor's running, the air temperature in that area is above 104? Yeah, I see some hands going up. You know, Not uncommon. Boiler rooms, places of that nature. In my market, even taking a motor outside certain days of the summer is going to exceed that by 10 or 11 degrees. Arizona, even worse. And so that becomes an issue. I had one, okay, think arc furnace, and we opened the door to the arc furnace for various reasons. Where does that heat go? Right out onto a couple of these other lines, motors. Things like that. Gear motors. Does putting a motor on a gearbox and attaching it to that now expose it to some additional heat from the gearbox? Here's one I see a lot. We changed out gearbox motors to more efficient motors, and now all these gearbox motors are failing prematurely because we didn't pay attention to insulation class or service factor on the new motors we bought. That type of thing. Proper ventilation. As an engineer, I chuckle at that one because we don't have any way to measure that. NEMA doesn't specify what that means. It just says it should be proper ventilation. So as I say to people, we know it when we see it, right? I can't give you an analysis thing, a measurement thing to say what that is. And a rigid mounting surface. Okay? Why is a rigid mounting surface important? Have you ever seen what a 10 horsepower three-phase motor does when it starts a pump? When it's just bolted down to a 2x8 about this long? It'll come off the ground about yay, you know. And then it goes right back down. So those are things that people can mess up. Protecting motors from electrical variations. Okay, so we would like to protect motors from being destroyed from relatively infrequent but normal events on the system. Trade-off protection of motors is always a trade-off between two mutually exclusive goals. Protect the motor from anything and everything. The more things I protect the motor from, the more chance of nuisance tripping I have in my facility. Could I get to a point where it's nuisance tripping so much that it's affecting production and my bonus and other people's bonus in the plant? Yes. That's the call I get a lot. We got these darn motors that are tripping off so often that we're not getting our goals and meeting our bonuses and everything. And so management wants it, the employees, we got to do something about it because it's not working. Now, I've seen companies that go the other extreme. We had so much nuisance tripping that we just pulled all the protection off the motor and said if we don't have anything that can trip, that motor's not going to shut off and shut off the line. And I always add then when I talk to them, until what? The smoke comes out. That's another strategy that we can look at. Somewhere in there, there's a happy medium of protecting from reasonable things at reasonable levels, but not causing us nuisance tripping. I've shared this with some of the folks in the room in past classes. Solid state electronic overloads. I can adjust the overload trip setting. You've all heard of thermostat wars in the office, right? Somebody's hot, they get up and adjust the thermostat for the AC to be cooler. 5 minutes later, somebody that's cold comes up and moves it back. I have now seen overload wars in plants. The person responsible for production comes by and cranks that overload adjustment to its maximum level so the motor won't trip. The person from physical plant responsible if the smoke comes out, comes by, sees that, cranks it the other way. So I saw a facilities manager that super glued those in place where he wanted them. Didn't even bother to put the little plastic cover over it, you know. I'll just super glue those there. Okay? So that becomes the challenge out there. So NEMA says, we talked about the plus or minus 10% voltage variation, plus or minus 5% of frequency. So a North American motor should be rated for 60 cycles per second. 5% of 60 cycles is a pretty wide frequency variation compared to the real world operation of what utilities run in. That is almost never ever a problem from grid power that you have to worry about. If the grid is at plus or minus 5% frequency variation, it's, if not shutting down already for a major blackout, tripping to have a major blackout. Where that can be an issue is when you're served from an on-site generator and the generator has a governor problem. And now your frequency could be quite a bit of a variation from 60. Okay, so that tends to be one of those things. Combination of voltage and frequency less than 10%. Supply phase voltage unbalance less than 1, we mentioned that. And harmonic distortion not to exceed 10% on the voltage side. So historically, the National Electric Code required us to put some devices in there. And that was typically, as I learned the industry, the business, what we considered motor protection. What did the code say we had to have in that motor circuit? And the code said we had to have overcurrent protection in the form of fuses and breakers, and overload protection in the form of heaters, a thermal relay, or today solid state or electronic overloads. That was all that's required by the code to say you've done a good enough job to protect from general safety and fire hazard things we're concerned about. Today there's an awful lot of optional protection equipment you could buy to add to a motor circuit, isn't there? Now when I started in the industry, some of you gray hairs like me might remember, if I wanted to put low voltage protection, that was a box, and I wired it in and I put it on the wall. And if I wanted single phase protection, I needed a phase failure relay, that was another box. And I wired it in and put it on the wall. And so pretty soon, if I wanted some of this, I had a whole bunch of boxes on the wall wired into the circuit. I bought them individually. Today, there are a lot of motor protector packages where I buy all that and it's already there in one box, which has made it easier and the prices have come down. So some people have always looked at low and high voltage protection as being important. Code doesn't require it, it's up to you. Phase failure relays to prevent motors from burning up during a single phasing event. How many of you use phase failure relays on your mission critical three-phase motors in your plant? We have more today than we did yesterday. We had a group of 49 yesterday and we had one company. Okay. Why do you have phase failure relays? Keep it from burning up the motors. It's like insurance. That's what I always like to tell. Okay, so they cost money. I need a budget. And the business people say, well, make your business case to me. Okay? Because we don't have them in another plant. Why should we have them here? Well, this is a device I'm putting in so that if and when I need it in the future, it's there to prevent my motors from burning up. And I don't know if or when that event's going to happen, but the chances overall are pretty good that sometime it's going to happen. The loss of one phase in a three-phase system. Well, could it ever happen that that co-op distribution line coming down the road in front of your facility has some type of an instant event where one of the lines breaks? Not all three, just one. Or back at the substation, one of the fuses blows on one of the phases, but the other two phases are still good. You've just been single-phased.
We had one of our three-phase transformers go out on the pole at 3 o'clock in the morning. Half the equipment kept running. The other half shut itself down. When they finally fixed it, everything that had shut down was safe, and the stuff that kept running destroyed itself. Yeah. Had to change 18 motors, unprotected.
Yeah. And so that's the, okay, it won't happen to me, or it might happen to me And I don't want to be the one that management's blaming if it happens next month, next year, 3 years from now, whatever. That becomes each side of the coin. I get a lot of calls from companies that have lost 15, 20, 30 motors because they got single-phased and not protected, wanting me to write a report to give to the utility to justify to the utility to pay for them. And I'm like, I've been through this rodeo before. It ain't happening. I guarantee you, customer on the other end of the phone, that utility had some kind of verbiage and language and something that somebody in your company assigned that said that phase failure, single phasing, is a normal but infrequent event on a three-phase power system, and it's up to you to protect your equipment from that happening. Okay. Sorry, but it's not going to happen. You're not going to get paid from the utility from doing that, for having them, even if they did it, their system. So that's one of those. Every place I go to do a class like this with big key account customers in it, it doesn't matter if it's Minnesota, Wisconsin, Arizona, Texas, Louisiana, the key account reps are always, and emphasize phase failure relays. Overcurrent protection, fuses and breakers. Motors are special. Why do we have to put fuses and breakers in a motor circuit? Okay, well, we want to protect from short circuit. I like to explain it to people this way. When I have a short circuit in my facility, there could be thousands or tens of thousands of amps flowing. Do I want thousands or tens of thousands of amps flowing for very long on a motor circuit? What's that going to do to my motor windings? Yeah, smoke comes out. So in a short circuit or fault event, I want a device protecting that motor that's going to see thousands or tens of thousands of amps and shut it off right now to protect that motor from that short. Okay? Now, the problem with doing that is that motor had an inrush current. So if I have to size that fuse or breaker big enough to get the inrush current through it without tripping and shutting the motor down every time I start it, I don't have any overload protection down here for a 10 or 15 or 20% above the nameplate level overload. By just using overcurrent device, it's big enough to get the motor started. So then I have to add, the code says I must add a separate overload device to protect that motor from a running overload, not the short or fault. The fuse or breaker protects the motor from the short or fault. The overload device protects it from a running overload above the nameplate level. And so typically I want to make sure that that device now has a sensitive enough trip time with the magnitude that it's not going to nuisance trip, but I'm not going to get into the motor damage area. And so coordinating that can be important. We talked about the optional motor protection. When I talk about phase reversal protection, my Aggie students are sitting there going, why would I care if we reverse the phases? And they already know that the motor will run backwards. What do we care if the motor runs backwards? So then I have to, enlighten them in terms of, okay, now think about some pumps. Do I want to run a pump backwards? Oh yeah. And then this is the one that really gets them and cements it home. I said, for you Aggie students here, I want you to think and follow me now. What if I do a phase reversal on the elevator motor? The buttons don't work right. Up is down and down is up. Yeah, I said, you'd never get to class if that happened. You just turn around and say the elevator was broke and walk away. Even if you figured out what was going on. So single phasing protection, as we mentioned. Why don't normal overload relays take a motor offline all the time in a single phasing event? Let's go back to the old school days. 3 heaters in that box, that starter, and a thermal element sensing the heat. So I have amps going through 3 different heaters producing heat, And that bimetallic element at a certain amount of heat is calibrated to open the contacts and shut the motor down. In a single phasing event, if I de-energize one of those legs, what happens to the amps on the remaining two? Because now they're still trying to bring enough amps into that motor to produce torque to turn the load. It'll run on two. So now I took the amps off one leg that's de-energized, and think about putting those amps split between the other two. What did I just do to the amps on the remaining two phases? They're higher than we want them to be. They might be higher than what the conductor is supposed to carry. Definitely the motor windings. Why doesn't the overload trip now from the higher amp on the remaining two phases?
Because you haven't raised total amperage.
I haven't raised the total amperage or heat. If I just took the amps and put them over here on the remaining two, is the heat from the two heaters much different than having the heat from the three heaters at lower amps? No. And we're tripping on heat, not amps, in that old heater system. And so a lot of those motors will just keep running because the overload doesn't think it's overloaded, even though now we put more amps on those two remaining phases than we would like to have on those. That's why you must, to guarantee that motor trips offline in a single phasing event, have that. Other motor protection, people use these sometimes. They're available in the market out there. Winding temperature monitors, protectors, current differential relays, vibration monitors and protectors, usually for very, very specific mission critical equipment where they want to know all kinds of information about that application, that motor, and how it's running.